Welcome to the Deep Dive. You sent us a really fascinating collection of material. This time looks like everything from detailed textbook chapters on aircraft systems.
Yeah, quite a bit to work through.
And your goal, as we understand it, is to get a really solid grasp on what's behind all those instruments in the cockpit.
That's the idea.
Well, that's exactly our mission too. To unpack the fundamental principles of aircraft instruments, explore how they've evolved a bit, and understand how they deliver that crucial information pilots need.
Precisely. We're going to explore the foundations, look at the different kinds of instruments, flight, engine, navigation, and really dig into the ingenious ways they sense and then display essential data.
So think of this as your streamlined guide.
Pretty much, to understanding the heart of the cockpit.
Okay, let's get started right at the beginning then. Your sources remind us that even the Wright brothers, back in their pioneering flights, they recognized the need for feedback from their machine.
Oh, absolutely.
Their Wright Flyer had a pretty rudimentary setup, didn't it?
It did, yeah. Their concerns were very practical, really. They needed to know the engine's revolutions per minute.
With a tachometer.
Right, a tachometer. And their speed through the air using an anemometer and just tracking their progress over time with a stopwatch.
Simple stuff, but essential even then.
Exactly. Even those basic instruments highlight their focus on the engine's operation and just the fundamental parameters of staying airborne.
Which leads us nicely to a core concept that your material emphasizes.
Yeah.
Every instrument system, no matter how complex it gets, has two fundamental parts.
That's it. First, you've got the sensing component, the bit that actually detects the change, like pressure or speed.
Okay.
And then you have the display, which presents that information so the pilot can, easily understand it.
Right.
In the older sort of analog instruments, these two functions are often combined right there in a single unit. That's a direct sensing instrument.
But we see remote sensing more and more, especially in modern planes. So, okay, let's unpack this. The sensing happens somewhere else on the aircraft, and the info gets sent to the cockpit.
That's the basic idea, yes. Remote sensing means the measurement happens right where it needs to say, out on the wing for airspeed or inside the engine for temperature.
Makes sense.
And that data is then sent to a separate display up on the flight deck. Traditionally, this was done using electrical wires carrying sensor signals, sometimes even pneumatic lines carrying actual pressure.
Pneumatic lines. Wow.
Yeah. And in older, more complex aircraft, well, this could result in a real tangle of wires and tubing behind the instrument panel.
Yikes, I bet troubleshooting that was fun. So what's the trend now? How's this information transferred these days?
The trend has definitely moved towards more efficient digital methods. But, it's important to remember that even with today's advanced digital systems, you still have this extensive network of connections, making sure all that crucial data gets where it needs to go.
Okay, now let's get into the different types of instruments. Your sources break them down into flight, engine, and navigation instruments. Let's start with flight instruments. What exactly are these telling the pilot?
Right. Flight instruments are fundamental. They're all about controlling the aircraft's attitude, its orientation in space, climbing, descending, banked, wings level.
Its posture in the air, sort of.
Exactly. As well as its altitude, its speed through the air, and its direction of travel.
And there are some basic ones you find in pretty much every aircraft, right?
Absolutely. The core group is the altimeter shows your height. Then the airspeed indicator tells you how fast you're moving relative to the air. And the magnetic direction indicator, basically a compass for your heading.
But that's just the basics. The picture gets clearer with some others.
Yes, definitely. Most aircraft also have an artificial horizon, gives you that visual reference of pitch and roll relative to the actual horizon.
Super important if you can't see the real one.
Crucial. Then there's a turn coordinator, indicating the rate of turn and any side slip, and a vertical speed indicator, showing your rate of climb or descent.
And your material mentions a basic T arrangement for these. What's the deal with that layout?
Yes. Over time, a standardized layout evolved in most cockpits. It arranges these key flight instruments in a T shape.
Okay.
And the artificial horizon is always top center, right in the pilot's and co-pilot's main line of sight.
Makes sense. Easy to find quickly.
Exactly. And what's really interesting is that even with modern glass cockpits, those digital displays, this basic arrangement, especially the central spot for the artificial horizon, is often kept.
So that standardization stuck around.
It did, even in digital cockpits. It just underscores the enduring human factor stuff in cockpit design for rapid scanning. Lets pilots find the critical info quickly, intuitively.
That makes perfect sense for quick checks.
Yeah.
Now, thinking about those original analog flight instruments, What powered them? It wasn't all electric back then, was it?
No, not at all. Initially, many relied on air pressure and gyroscopes, and that was deliberate, actually.
Redundancy.
Precisely. A backup in case of electrical failure. Now, obviously, advancements in electrical systems mean modern aircraft have very reliable electric primary and secondary instrument systems.
But that backup idea is still critical, right?
Absolutely vital. That's why you'll often still find a pneumatic altimeter, maybe a gyro-driven artificial horizon, and definitely a magnetic direction indicator tucked away in the panel, even with all the fancy electronic displays.
Just in case.
Just in case. Essential backups if electrical power goes out or a primary digital display fails.
Okay, moving on to engine instruments. These seem pretty straightforward, telling the pilot how the engines are doing.
Pretty much. Engine instruments measure the critical operating parameters, typically things like quantity fuel and oil levels.
How much you've got left?
Right. And pressure, like oil pressure, speed, like engine RPM, and various important temperatures.
So in the cockpit, you'd expect to see gauges for fuel, oil, tachometers for engine speed, and temperature gauges for, say, the oil.
Exactly. Those are the common ones. They let pilots constantly monitor the engine's health and performance throughout the flight.
And then we have navigation instruments. These are all about getting from A to B.
Yes, and navigation instruments provide the info pilots need to guide the aircraft along their desired course. Traditionally, this was really basic stuff. Like an accurate clock and a magnetic compass.
But those have limitations, don't they? Especially for complex flights or long distances.
Oh, absolutely. Trying to manually figure out your position and progress using just airspeed, wind estimates, a clock, and a compass, well, it's largely been replaced.
By radio navigation and GPS, I assume.
Exactly. Radio-based systems and, of course, GPS, global positioning systems, use that network of satellites orbiting Earth to triangulate the aircraft's precise location.
And that technology is baked into modern instruments now.
Seamlessly integrated into many modern instrument packages. Gives you highly accurate navigation.
It's amazing, really. From a stopwatch and compass to satellites. Now, your sources also mention classifying instruments by how they work, their operating principle. Quick overview.
Sure. You've got mechanical instruments directly measuring things like pressure and temperature using physical parts.
Okay.
Then magnetic and electrical ones using magnetism and electricity. Gyroscopic instruments use spinning rotors for attitude and direction.
Right, gyros.
And finally, the modern stuff. Solid-state instruments and complex computer-based systems doing everything electronically.
Let's dive a bit deeper into one category. Pressure sensing instruments. Your material really stresses how critical these are.
They are. Absolutely fundamental for both safe flight and monitoring the engine. They can be direct reading or part of a remote system, but they're crucial for giving the pilot vital info.
And they use some clever mechanisms.
Very ingenious mechanisms, yeah.
Yeah.
They can detect and respond accurately to even tiny changes in air or fluid pressure.
Okay, and when we talk pressure, there are key concepts like gauge pressure versus absolute pressure.
Mm-hmm.
What's the difference, and why is gauge pressure often more useful in aviation?
Right. Gauge pressure is pressure relative to whatever the surrounding atmospheric pressure is. Absolute pressure is relative to a perfect vacuum.
Okay.
In aviation, gauge pressure is often more practical because it gives you a direct sense of the working pressure in a system, regardless of altitude changes.
Ah, I see.
Your material has a great example with aircraft tires. The gauge pressure you read when inflating them will be the same at sea level or a high-altitude airport. That ensures the tire has the correct operational pressure, even though the absolute pressure inside is different because the starting atmospheric pressure was different.
So gauge pressure gives you that consistent, usable number for operations.
Exactly. That's the key insight.
Your sources also mention differential pressure. What's that about?
Differential pressure is just when an instrument measures the difference between two separate pressures to get meaningful information.
Like the airspeed indicator.
Perfect example. It measures the difference between ram air pressure, the pressure from moving through the air, and the ambient static pressure to figure out airspeed.
Okay. Any other examples?
The engine pressure ratio, or EPR gauge, in turbine engines. It compares the total pressure at the engine inlet with the total pressure at the exhaust.
To indicate thrust.
Exactly. Gives an indication of thrust output.
And then there's standard pressure. What is that and why is it so important, especially flying high up?
Standard pressure is a universal reference value for atmospheric pressure. It's 29.92 inches of mercury, or 113.2 hectopascals, or 14.7 psi.
A globally agreed number.
Right. It's part of the standard atmosphere model used in aviation. And the key thing is, above 18,000 feet in the U.S., all aircraft must set their altimeters to this standard pressure.
Why is that?
It ensures everyone's altitude readings are based on the same reference. Absolutely critical for keeping planes safely separated vertically at those higher flight levels.
So consistency for air traffic control.
That's the main driver. Standard pressure provides that consistent altitude reference essential for safety up there.
Got it. Now, how do the instruments actually sense these pressure changes? What are the basic mechanisms?
Your sources point to three main types: the Borden tube, the diaphragm or bellows, and modern solid-state sensors.
Let's start with the Borden tube. Sounds interesting. How does that work?
It's pretty clever, actually. It's basically a curved, hollow tube sealed at one end, connected to the pressure source at the other.
Oh.
When pressure goes in, the tube tries to straighten out, kind of like a party horn uncurling.
Okay.
This tiny mechanical movement is then linked through gears and levers to a pointer on the dial. So the pointer moves to show the pressure.
And what's it used for?
Commonly used for measuring liquid and gas pressures, engine oil, hydraulic fluid, oxygen, even D-spoots. And interestingly, because the pressure of a heated liquid or gas also increases with temperature, you can adapt a Borden tube to indirectly measure temperature too, just by calibrating the scale differently. You see that in some oil temp gauges.
That is clever engineering. Relies purely on physical principles.
Exactly. Shows that early ingenuity.
Okay, what about diaphragms and bellows? How do they sense pressure?
Diaphragms are flexible membranes, like little drums. Bellows are more like, well, like an accordion, a series of connected chambers.
Right.
When the pressure on one side changes relative to the other, or relative to a sealed reference, they move, they deflect, or expand and contract.
And that movement drives the gauge.
It can directly drive a pointer, or it can generate an electrical signal in a remote system. A key variation is the aneroid.
Ah, the aneroid. Heard that term.
It's a sealed diaphragm, but it's been evacuated almost a perfect vacuum inside. Aneroids are the heart of things like altimeters and manifold pressure gauges.
And bellows.
It's often used in differential pressure gauges, designed to compare two different pressure inputs.
And the third type was solid-state sensors, the modern ones.
Right. These use electronic components whose electrical properties, like resistance or capacitance, change directly when pressure is applied.
So no moving parts, really.
Not in the sensing element itself. Electronic circuits measure these property changes very precisely. The resulting signal is processed and sent to a digital display. Very accurate, often very compact.
Okay, let's look at some specific pressure instruments. Manifold pressure, what's that telling the pilot?
Manifold pressure measures the absolute pressure inside the intake manifold of a piston engine. It's a primary indicator of the engine's power output.
How does the gauge work?
It usually uses an aneroid directly exposed to the manifold pressure. As throttle and load change, the pressure changes, the aneroid expands or contracts.
And moves the pointer via linkage.
Exactly. Calibrated in inches of mercury.
Got it. And engine pressure ratio, EPR.
Yeah.
Matched it for turbine engines. Vital measurement.
Correct. Vital for turbines directly relates to thrust. The EPR gauge is a differential pressure instrument. It continuously compares the total air pressure at the engine inlet with the total pressure at the exhaust.
And how is that displayed?
A pressure transducer, often in the engine nacelle, senses these pressures. The ratio is calculated and shown on the EPR gauge, either analog pointer or digital readout.
What about fuel and hydraulic pressure? Seems incredibly important to monitor those.
Absolutely critical. Fuel pressure ensures the engine gets enough fuel. Hydraulic pressure is vital for landing gear, flight controls, brakes, lots of systems.
And you wouldn't want fuel lines in the cockpit, right?
Definitely not. Big fire hazard.
Yeah.
So remote sensing using synchro systems and electrical signals is the standard way for both fuel and hydraulic pressure.
Okay.
Sometimes, instead of fuel pressure, they monitor fuel flow rate as an alternative check on the fuel system. Hydraulic gauges, though, you often find them in the cockpit and near the system, servicing points for maintenance checks.
And then vacuum pressure or suction. You mentioned it earlier for older gyro instruments.
That's right. Measured by a suction gauge, usually in inches of mercury. It was used to spin the gyros in early attitude indicators and directional gyros.
How does the gauge work?
It measures the pressure difference between the inside of the gyro vacuum system and the ambient air. Keeping the right vacuum level is crucial for the gyros to spin at the correct speed for accuracy.
Makes sense. Lastly, pressure switches. They're not gauges showing a value, but more like on-off things.
Exactly. A pressure switch just opens or closes an electrical circuit when pressure hits a specific set point.
Like a warning light.
Perfect example, the low oil pressure warning light. If oil pressure drops too low, the switch closes the circuit, light comes on, pilot knows there's a problem. Simple, but critical.
Now, a system that relies heavily on several of these pressure concepts is the pitot-static system. Sounds like it's really central to how many flight instruments work.
It really is. The pitot-static system basically gathers and distributes the air pressures needed for key flight instruments.
What are the main parts?
It consists of a pitot tube usually mounted outside on a wing or the fuselage. It captures ram air pressure, the pressure from moving forward.
Okay, the pitot tube for ram air. What else?
It also has one or more static vents, usually flush-mounted on the side of the fuselage in smooth airflow. These sense the ambient static air pressure.
And these two parts, pitot and static, are often in different places.
Yes, typically separate locations for accuracy. Bigger aircraft, especially multi-engine or pressurized ones, can have complex systems. Multiple static vents placed strategically to minimize errors from airflow variations.
How do they manage multiple vents?
Often connected with Y-tubing to sort of average out any local pressure fluctuations and to stop ice blocking them.
Heating elements.
Yep. Both the pitot tube and static vents often have internal heating elements. Very important.
What about smaller, unpressurized planes? Is there a backup for the static source?
Yeah, many have an alternate static source, usually just a port inside the cabin. The pilot can select it if the main vents get blocked.
Provides a backup pressure reading. And in modern, complex aircraft, how is all this pitot-static data managed and used?
Well, in those planes, the pressure info doesn't just go straight to the gauges. It also feeds the autopilot, various onboard computers managing flight controls, navigation.
So it's integrated.
Highly integrated. Air data computers, ADCs, are key here. They take the raw pressure data, process it with fancy algorithms. Calculations to provide calibrated airspeed, altitude, vertical speed, and other data to lots of systems and the electronic displays.
Okay, let's talk about the specific instruments that use the pitot-static system, starting with the altimeter. Tells us altitude, but how does it use pressure?
Right. The altimeter is basically a direct reading absolute pressure gauge. At its heart is that aneroid we talked about, the sealed, evacuated diaphragm.
Okay.
Static air pressure from the static vents is fed into the altimeter's airtight case surrounding the aneroid.
So the aneroid is inside the case with static pressure outside it.
Exactly. As the plane climbs, atmospheric pressure drops. The higher pressure still inside the sealed aneroid causes it to expand. This expansion is mechanically linked through levers and gears to the pointer on the dial, which is calibrated in feet to show altitude.
And descending.
The opposite. Static pressure increases, compresses the aneroid, pointer moves the other way, indicating lower altitude. So it's translating static pressure changes into altitude based on that standard atmosphere model.
So it relies directly on that pressure-altitude relationship. But I know it's not quite that simple. You need to set the altimeter right.
Absolutely right, because actual atmospheric pressure changes constantly with weather. Just using a fixed internal reference isn't enough for accurate altitude readings relative to sea level or an airport.
So you need the local pressure.
Exactly. That's where the altimeter setting comes in. Analog altimeters have that little window, the Colesman window, where the pilot dials in the current local pressure from a weather report.
Below 18,000 feet, you use the local setting.
Correct. In the U.S., below 18,000 feet, use the local setting. Above that, everyone switches to the standard pressure setting, 29.92 inches of mercury.
For that standard eye separation we talked about.
Precisely.
And using that standard setting above 18,000 gives us pressure altitude.
That's the term, yes. Pressure altitude is the altitude your altimeter shows when set to 29.92. It's that standardized reference used by ATC and for performance calculations.
Your material also mentions temperature affecting altimeter accuracy. How does that work?
Well, the aneroids are usually metal, and metal's elasticity changes with temperature.
So extreme cold or heat could throw it off slightly?
It can, yes, leading to small inaccuracies. To counter this, many sensitive altimeters have a little bimetallic compensating device inside.
Bimetallic, like the thermometer.
Same principle. Two metals with different expansion rates. It mechanically adjusts the linkage based on temperature, helping to correct for the aneroid's temperature-induced changes.
Clever. Now, the altimeter doesn't show it directly, But density altitude is also critical for performance, isn't it?
Very critical. Density altitude is basically pressure altitude corrected for non-standard temperature.
So it reflects the actual air density.
Exactly, and that directly impacts performance, takeoff distance, climb rate, true airspeed, the air's thickness, basically. Pilots calculate it using charts or computers based on pressure altitude and the outside air temp.
Are there other things besides temperature that can mess with altimeter accuracy?
Oh, sure. Several potential errors. There can be mechanical scale errors within the instrument itself, calibration issues.
Okay.
Leaks in the static system are a big one. They lead to wrong pressure readings at the altimeter.
Causes wrong altitude readings.
Right. And in older mechanical ones, you could get hysteresis, sort of a temporary stickiness in the diaphragm after flying level for a long time. It might lag slightly when pressure changes.
Okay. Let's move on to the vertical speed indicator, the VSI.
Yeah.
How does that show climb or descent rate?
The VSI is a differential pressure gauge. It compares two slightly different static pressures.
How does it do that?
Well, one static pressure line goes directly to a sealed diaphragm inside the instrument. The other static pressure source goes into the airtight case around the diaphragm, but it has to pass through a tiny, precisely calibrated hole, an orifice. This creates a small delay in how quickly the pressure inside the case equalizes with changes in outside static pressure.
Calibrated leak.
Exactly. So if the plane starts climbing or descending, there's a momentary pressure difference between the insti pressure inside the diaphragm and the slightly delayed pressure in the case.
And that difference moves the diaphragm.
Right. Causes it to expand or contract, moving the pointer via linkage, indicating vertical speed in feet per minute. That calibrated leak is the key. It creates the lag needed to show a rate of change.
So when you're in a steady climb or descent, the pressure difference stabilizes, and the VSI gives a steady reading.
Precisely. And there's usually a little screw on the front, a zeroing adjustment to calibrate it to read 0 when you're on the ground and not moving vertically.
Are there more advanced versions?
Yes, some systems use instantaneous VSIs, often using accelerometers, which react much faster without the inherent lag of the traditional type. And gliders use very sensitive variometers, often comparing static pressure to a trapped reference pressure to detect tiny altitude changes.
Okay, finally for this section, airspeed indicators. Telling us how fast we're moving through the air, also using differential pressure from the pitot-static system.
Yes, another crucial one. Also a differential pressure gauge. It measures the difference between the ram air pressure, pitot pressure from the pitot tube, and the ambient static pressure from the static vents.
How's it constructed?
The pitot pressure goes into a sealed diaphragm inside the case. The static pressure fills the case around the diaphragm.
So similar setup to the VSI, but using pitot versus static.
Kind of, yeah. As speed changes, the ram pressure changes, causing the diaphragm to expand or contract. That movement is linked to the pointer, indicating airspeed in knots or move.
Now, I know there are different kinds of airspeed indicated, calibrated. What's the difference?
Good point. Indicated airspeed, IAS, is just what you read directly off the dial.
Simple enough.
Calibrated airspeed, CAS, is IAS corrected for certain errors in the pitot-static system itself.
Like what?
Things like position error, where the pitot tube and static vents are located, might not sense perfectly undisturbed air at all angles of attack. Also, minor imperfections in the instrument's scale.
So CAS is more accurate.
Generally, yes. Older planes often have a correction card near the gauge to convert IAS to CAS. Modern digital systems with an ADC do this correction automatically. So pilots need to know which speed they're looking at for different things, right?
Absolutely critical. And then there's true airspeed, TAS. Our actual speed through the air mass. How's that figured out?
TAS accounts for air density, which changes a lot with altitude and temperature. Digital systems with an ADC calculate TAS by taking CAS and correcting it for that air density, using inputs from the pitot-static system and an outside air temperature sensor.
And TAS is important for?
Navigation, definitely. And accurate performance calculations, especially higher up where the air is thin. It's your true speed relative to the air you're flying through.
Your material also touches on monitoring airspeed relative to the speed of sound, especially for high-performance planes.
Yes, that's critical. As a plane nears the speed of sound, which itself changes with altitude and temp airflow over parts of the plane, can go supersonic, even if the plane itself is subsonic.
creating shockwaves.
Exactly, which can seriously affect control, performance, even structural integrity. That's why fast jets have a critical Mach number, MCRIT.
MCRIT.
The highest Mach number where airflow everywhere around the plane stays subsonic. Mach number is just your true airspeed divided by the local speed of sound.
So they need instruments for that.
Right. Many high-performance planes have MCRITers, basically airspeed indicators calibrated in Mach or combination Mach speed indicators to help pilots stay within safe limits.
So all these pressure instruments work together, feeding pilots crucial real-time flight info. Okay, let's shift focus slightly. Remote sensing instrument systems more generally. How do they typically work?
Well, the basic idea, as we touched on, is the sensing happens somewhere away from the cockpit.
Right.
That measurement is converted to an electrical signal sent via wires to an indicator unit on the flight deck for the pilot to see.
So what are the main parts?
Typically, you have the sensing device itself, maybe a temperature probe on the engine. Then a transmitter unit takes the sensor output, converts it to a proportional electrical signal. And finally, the indicator in the cockpit, all connected by wires.
Allowing remote indication of mechanical positions or pressures.
Exactly. Crucial for safety and efficiency in many systems.
And in modern digital aircraft, how does that data flow work?
In those, the sensors often feed raw data to dedicated computers. Like PITA static info goes to the air data computer, engine sensor data goes to the engine monitoring computer.
The computers process it.
Right. They process the raw data, apply corrections, calibrations, whatever's needed. Then they send the final digital info to the flight deck displays over digital data buses.
So instead of driving a pointer directly,
the digital signals tell the electronic screens how to display the information, maybe as a number, or showing the position of a control surface graphically.
Your material specifically mentions synchro-type remote indicating instruments. What are those and why are they useful?
Synchro systems. They're a specific type of electrical system used a lot in aviation to send information remotely, often the angle of something mechanical or a pressure reading.
Synchro, like synchronous.
Exactly. Comes from synchronous. They usually have two main parts, a transmitter and an indicator that work together, synchronized. They rely on basic electromagnetism, the link between electricity and magnetic fields.
Are there different kinds?
Yeah. The common ones mentioned are the DC CELSA system for planes with DC electrical systems and various AC synchro systems, like autosyn and magnesyn, used in planes with AC power.
Let's look at the DC Celsin first. How does it work for something like, say, landing gear position?
Okay, for landing gear, a transmitter unit is linked mechanically to the gear mechanism itself. Inside the transmitter, there's a circular resistance winding.
Like a rheostat.
Sort of. And a rotating contact arm, a wiper, moves across this winding as the gear goes up or down. Its position determines the voltage picked off from different points.
And that voltage goes to the cockpit.
Right. Via wires to the indicator. The indicator usually has 3 fixed toroidal windings around a central rotor with a permanent magnet attached to the pointer.
Okay.
The currents flowing through those indicator windings create a magnetic field. The permanent magnet rotor aligns with this field, making the pointer show the gear position.
And it can show locked positions, too.
Yeah, often they add little limit switches. When the gear locks up or down, a switch closes, adding resistance or changing the circuit, which shifts the magnetic field just enough to give a distinct locked indication on the display.
That's pretty neat.
Yeah.
A reliable way to show mechanical position remotely. Now, what about AC synchros like autosyn and magnesyn? How are they different?
They work on similar principles, but use AC power, not DC. Instead of current through brushes and windings like DC Celsin, they use electromagnetic induction.
Induction, okay.
In a magnesyn system, both transmitter and indicator rotors have permanent magnets. Autosyn systems use electromagnets for their rotors.
But the principle is similar.
Yeah. The transmitter rotor is linked to whatever's being monitored like a flap. As it turns, it induces varying AC currents in stator coils in the transmitter.
And those currents go to the indicator.
Right. To matching stator coils in the indicator. They create a magnetic field pattern that mirrors the transmitter's field. The indicator's rotor and the pointer aligns with that field, matching the transmitter rotor's position.
Where are these AC systems typically used?
Often in higher performance aircraft for lots of things remotely showing flight control positions, feeding heading info to directional indicators, even in autopilots.
Your material also note how synchros are used for remote fuel and oil pressure indication. Makes sense for safety, avoiding fluid lines in the cockpit.
Exactly. You put the synchro transmitter where the pressure is near the engine for oil, near the tank for fuel. No need for long, vulnerable fluid lines to the cockpit.
How does the transmitter work for pressure?
Inside the transmitter, a pressure sensor like a bellows or diaphragm is linked mechanically to the synchro's rotor. Pressure changes move the bellows, which turns the rotor through a linkage.
Changing the electrical signals.
Right. The transmitter sends altered signals to the indicator in the cockpit, which moves its pointer to show the pressure value. On multi-engine planes, you might have multiple synchro systems in one gauge housing showing pressure for each engine on one dial.
So synchros are a really versatile way to get info electrically and remotely.
Okay, let's shift to instruments that directly show mechanical movement.
Right. While synchros can do that remotely, there are other ways too, direct and indirect.
Let's start with tachometers, essential for engine and rotor speed, right? Absolutely crucial. Tachometers show rotational speed RPM, engine crankshaft speed, or for helicopters, main and tail rotor speed.
And many have hour meters too.
Yeah, lots of Tatches and piston engine planes have built-in hour meters that just log total engine operating time. There are basically two main types, mechanical and electrical.
How do mechanical tachs work?
Usually found in smaller single-engine planes where the engine isn't too far from the panel, there's a direct mechanical link, a flexible drive shaft, attached cable from the engine to the gauge.
And inside the gauge?
The shaft spins a flyweight assembly. As speed increases, centrifugal force pushes the weights out. This movement is geared to move the pointer on the dial.
Simple mechanics?
Pretty much. Another mechanical type uses a magnetic drag cup instead of flyweights. A magnet spun by the engine induces currents in a nearby cup, dragging it around against a spring, moving the pointer.
Okay. What about electrical tachometers?
These use a separate tachometer generator mounted on the engine. As the engine spins, it drives this generator, which produces an electrical signal AC or DC, whose frequency or voltage is proportional to RPM.
And that signal goes to the cockpit indicator.
Right, via wires to a synchronous electric motor inside the indicator. This motor spins at a speed matching the generator's signal frequency,
Driving the pointer.
usually via another magnetic drag cup or disc mechanism, similar to the mechanical type, to display the RPM. Lots of different generator designs and mounting types exist.
And for multi-engine planes, often dual tachometers.
Correct. A dual tach houses two independent mechanisms in one case. Shows RPM for two engines, maybe on one dual scale dial or two separate ones.
And in helicopters.
Often used there too to show engine RPM and main rotor RPM simultaneously. Comparing the two can indicate clutch slippage.
Now, your material mentions tachometer probes in turbine engines. How are they different?
These are different. No moving parts in the probe itself. They're sealed units mounted near a rotating part in the engine, like a compressor shaft.
How do they send speed then?
They generate a magnetic field. As a toothed gear wheel on the shaft spins past the probe's pole pieces, it disturbs the magnetic field cyclically.
Inducing voltage pulses.
Exactly. Voltage pulses in coils inside the probe. The frequency and amplitude of these pulses are proportional to the engine speed.
But the signal needs processing.
Usually, yes, it's a low-level signal, so it typically needs processing and amplification by a remote electronic box before it can drive an indicator or feed into other systems like autothrottles or FAA-H-8083-31B.
Next up, the synchroscope. Sounds like it's for synchronizing multiple engines.
That's exactly its job. A synchroscope helps pilots of multi-engine planes match the RPMs of their engines.
How does it work?
It takes the output signals from the tach generators of the engines being synced and compares their frequencies. Inside, there's usually a small electric motor that gets current from both tach circuits.
And the pointer move based on the frequency difference.
Right. The phase relationship between the two AC signals determines which way the pointer or a rotating disc moves. If one engine's faster, it shows which one. When they're perfectly synced, the pointer stops moving.
So the pilot adjusts throttles until it stops.
Precisely. Often one engine is the master, and the synchroscope shows the speed of the others relative to it.
Okay, let's move to accelerometers. They measure acceleration forces. What's their role in aircraft instruments?
Well, accelerometers measure the G-forces acting on the plane. In terms of cockpit displays, they're mainly in high-performance and aerobatic aircraft to monitor the loads on the airframe and occupants during maneuvers.
Important for staying within structural limits.
And physiological limits, yes. Crucial info. Multi-axis accelerometers are also fundamental parts of inertial reference or navigation systems, IRS or INS.
How do those work?
They continuously calculate the aircraft's position, velocity, and attitude based on measured accelerations in all three dimensions. Modern ones are often electric or digital, using solid-state sensors like piezoelectric crystals.
Piezoelectric?
Yeah, they generate an electrical signal proportional to the acceleration force applied. That signal is processed and displayed or used by other systems like flight control computers.
Stall warning device is absolutely critical for safety. Your material mentions a couple of types.
Yes, vital devices. They alert the pilot when the angle of attack is getting dangerously high, nearing a stall. One common type is the reed type.
How does that work?
It's usually in a small opening on the wing's leading edge. As angle of attack increases near the stall, airflow separation creates low pressure, suction on the wing's upper surface.
And that suction does something.
It pulls air through a little passage inside the wing. This airflow makes a thin metal reed vibrate rapidly.
Creating a sound.
Exactly. A distinct buzzing or whistling sound in the cockpit. A clear warning.
And the other type mentioned uses an audible tone or horn?
Right. That one uses an electric switch, also near the leading edge, near the stagnation point.
Stagnation point.
Where the airflow splits over the wing. This system usually has a small, spring-loaded tab or vane sticking out slightly. At normal angles of attack, airflow holds the tab down, keeping the switch open. But as angle of attack increases towards the stall, the stagnation point shifts, airflow changes, and the tab flips up.
Closing the switch.
Right. Closing the switch activates a horn or light in the cockpit. Immediate alert. Approaching stall.
Okay, now we need to cover temperature instruments. Lots of things need temperature monitoring on a plane, it seems.
Absolutely. Crucial for safe and efficient operation. Things like engine oil temp, carb air temp on piston engines, inlet air temp on turbines, outside air temp, OAT, cylinder head temp, CHT, on pistons, cabin heater ducts, and exhaust gas temp, EGT, or turbine inlet temp, TIT, on turbines.
Quite a list. How are these measured?
Various ways. There are non-electric types and electric types.
Let's start with the non-electric ones.
One common one is the bimetallic strip thermometer. Uses a strip made of two different metals bonded together.
Metals that expand differently with heat.
Exactly. Different coefficients of thermal expansion. When temp changes, one metal expands or contracts more, causing the strip to bend or coil.
And that moves the pointer.
Right. Mechanically linked to the pointer on a calibrated scale. You often see these for direct reading OAT gauges, with a little probe sticking outside.
And the other non-electric type was a Borden tube thermometer. Using a Borden tube for temp.
Yeah, similar to the pressure gauge application. You have a sealed sensing bulb filled with a volatile liquid connected to the Borden tube by a thin capillary tube.
How does that measure temp?
Temperature changes around the bulb change the vapor pressure of the liquid inside. This pressure change travels through the capillary tube to the Borden tube.
Making the tube straighten or curl.
Precisely. Just like with direct pressure, the movement is linked to a pointer on a temperature-calibrated dial, sometimes used for things like oil temp.
Okay, now for the electrical methods. What are the main types of electrical temperature sensors?
Two primary types commonly used, electrical resistance thermometers, sometimes called RTDs, and thermocouples.
How do resistance thermometers work?
Based on the principle that the electrical resistance of certain metals changes predictably with temperature. They use a small, heat-sensitive resistor element made of a specific alloy.
So, measure the resistance, know the temperature.
Essentially, yes. The change in resistance is measured by circuitry in the cockpit indicator. The dial is calibrated in temperature units, usually used for lower to medium temp ranges.
What kind of indicator circuit?
A common type is the ratiometer. Uses two coils and a permanent magnet. Current flow changes based on the sensing bulb's resistance, altering the magnetic fields, causing the magnet and pointer to rotate.
And thermocouples. You said they're for higher temperatures like CHT and EGT.
That's correct. Designed for very high temps. They work on the thermoelectric effect.
Which is?
When two dissimilar metals are joined at two junctions and the junctions are at different temperatures, a small voltage millivolts is produced across the open ends.
And the voltage relates to the temperature difference.
Exactly. Proportional to the difference between the hot junction, where you're measuring, and the cold junction, usually inside the instrument case. Different metal pairs, like chromo-alumel, are used for different ranges.
What do the junctions look like?
The hot junction can be various shapes, like a gasket under a spark plug for CHT, or a bayonet type inserted into the exhaust for EGT.
And the cold junction needs compensation.
Yes, because the output voltage depends on the difference. The instrument needs to compensate for changes in its own temperature, the cold junction, often done with a bimetallic spring mechanism. Modern planes might use LED displays for CHT too.
What about measuring the really hot temperatures in turbines, like EGT and TIT?
For turbines, measuring EGT and TIT accurately is critical for performance and preventing damage. These systems usually use multiple thermocouples placed around the turbine casing or exhaust duct to get an average reading.
And the signal needs boosting.
Yes, the small millivolt signals are usually amplified electronically to drive servo motors for analog pointers or to provide digital readouts.
What about TIT specifically?
Turbine inlet temp systems measure the gas temp right before the turbine. Also use thermocouples, often dual probes at each point for redundancy, one set for the cockpit, another for engine control systems.
And finally, total air temperature, TO. Sounds specialized for high speed.
It is. TAT is the static air temperature plus the temperature rise from ram effect or kinetic heating at high speed.
Tricky to measure accurately.
Yes. Challenges due to air friction on the probe, compressibility effects. Specialized TAT probes are aerodynamically designed to minimize these errors and capture the air's total energy, which relates to TAT.
Knee heating too.
Often heated to prevent icing, but designed so the heating doesn't skew the reading. Some even use engine bleed air to manage airflow over the sensor. In digital systems, the TAT signal goes to the ADC for processing.
Okay, covered a lot of ground there. Let's turn to magnetic compasses now. Fundamental for heading.
The most basic direction finder, really, works because a free-floating magnet aligns with the Earth's magnetic field.
What's inside a typical aircraft compass?
Usually one or more magnets attached to a float with a compass card marked with headings, all housed in a sealed case filled with damping liquid, like oil, to keep it steady.
And how do you read it?
There's a vertical reference line, the lubber line, on the front of the case. You read the heading on the card that's aligned with the lubber line.
What about temperature changes affecting the liquid?
There's usually a bellows or diaphragm inside to allow the liquid to expand and contract without breaking the case.
But compasses aren't perfectly accurate, right? Errors like deviation and variation.
Absolutely correct. Deviation is error caused by the aircraft's own magnetic fields from metal parts, electrical currents.
How do you deal with that?
Through a process called swinging the compass. You put the plane on a compass rose marked with known headings, turn it to each heading, note the compass reading, and adjust small compensating magnets inside the compass to minimize the error.
What about leftover error?
Residual errors are recorded on a compass correction card, usually mounted near the compass. The pilot uses this card to correct the readings.
Okay, that's deviation. What's variation?
Variation is natural. It's the angle between magnetic north, where the compass points, and true north, geographic pole used on charts. It varies depending on where you are on Earth.
How do pilots handle variation?
Charts show lines of equal variation, isogonic lines. Pilots add or subtract the local variation to convert between magnetic and true headings for navigation.
And then there's dip error, especially near the poles.
Yes. Near the magnetic poles, the Earth's field lines dip down more vertically. This vertical component makes the compass magnets try to dip too.
Causing errors.
Yes. Acceleration error. On east-west headings, accelerating makes the compass lag, indicating a turn north. Decelerating indicates a turn south. And turning error. On north headings, turning makes the compass lag. On south headings, it leads the turn, worse near the poles, and on east-west headings.
Your material also mentioned the compass card seeming to rotate the wrong way during turns.
Yeah. That's a visual quirk of the standard direct reading compass. You're looking at the back of the card, effectively. When you turn left towards lower numbers, the numbers physically on your left are actually increasing. It feels counterintuitive.
What about the vertical magnetic compass? Does it fix that?
It does. It uses gears to rotate a cylindrical card horizontally. So turn right, numbers on the right increase more intuitive. Many use eddy current damping instead of liquid.
Still subject to deviation and variation, though.
Oh yes, still needs compensation, but no manual heading knob like a gyro.
And for bigger planes, remote indicating compass systems, how do they improve things?
To minimize deviation, the main magnetic sensor is put somewhere magnetically clean, like a wingtip or tail.
Away from interference.
Right. It sends the heading info electrically to the cockpit indicator, usually using a synchro system, often Magnuson type. The remote sensor is the transmitter. The cockpit gauge is the receiver.
Finally, the remote indicating slaved gyro compass, or flux gate compass. Sounds like a hybrid system.
That's a great way to put it. Combines the stability of a directional gyro with the direction finding of a remote magnetic sensor, the flux valve or flux gate.
How does the flux valve work?
It usually has a permeable core, like a little spider shape, with pickup coils wound around it. The Earth's magnetic field induces AC signals in these coils. The signal characteristics depend on the valve's orientation to magnetic north.
And these signals go where?
To a directional gyro, DG, and amplifier unit. This unit uses the flux valve signals to constantly correct any drift in the DG, slaving the gyro to the magnetic heading.
Providing a stable heading.
Very stable and accurate. The gyro's heading is then sent electrically, often via autosyn, to the cockpit indicator, usually a vertical card. It avoids most standard compass errors, often integrated with radio nav info in an RMI, radiomagnetic indicator.
Now, gyroscopic instruments are so crucial, especially in cloud or low visibility. What powers these gyros?
Right, they need to spin fast for rigidity. Historically, power came from vacuum systems, electrical power, or sometimes pressure systems.
Let's talk vacuum systems first, early methods.
Sometimes just a venturi tube stuck outside in the airflow. Air rushing through created low pressure to spin the gyros.
Red limited.
Very. Depended on airspeed, density, prone to icing. Engine-driven vacuum pumps became standard, wet, oil lubricated, or dry self-lubricating types.
I said this.
Needs regulation.
Yep. A vacuum regulator maintains the correct suction. Big downside. Engine failure means loss of vacuum, loss of gyro instruments.
So backups are needed.
Exactly why many planes with vacuum gyros have at least one electric backup, like the turn coordinator. And there's a suction gauge in the cockpit to monitor the system's health. Correct suction means gyros spin right.
And the basic mechanics of a gyro.
It's a rotor, a weighted wheel on an axle, spinning freely. Supported by gimbals, pivoted frames allowing a rotation. Captive gyro has one axis of freedom, free gyro has two.
And the key properties. Rigidity in space, the spinning rotor wants to keep its orientation. Depends on weight, speed, how far weight is from center, and low friction, and precession reacting to force at 90 degrees to the force and 90 degrees to the spin axis.
Your material also mentions ring laser gyros. Modern tech. How do they work?
Yeah, RLGs are totally different. No spinning mass. They use the Sagnac effect from relativity theory.
Sagnac effect.
Basically, they shoot two laser beams in opposite directions around a closed path, usually a triangle or square cavity in a glass block.
Okay.
When stationary, the beams travel the same path length, same frequency. When it rotates, one beam's path gets slightly longer, the other slightly shorter. This creates a tiny frequency difference.
And that difference measures rotation.
Exactly. The frequency difference is proportional to the rotation rate. Very accurate. They have a little dither motor to vibrate the block slightly, preventing lock-in at very low rotation rates.
Okay, let's look at specific gyro instruments. The attitude indicator or artificial horizon.
The AI, primary flight instrument, uses a gyro to show the plane's attitude, pitch, and roll relative to the real horizon. Can be vacuum or electrically driven.
What's the display look like?
Usually a miniature airplane fixed to the case, and a horizon bar that moves behind it, showing pitch and bank against a blue sky, brown ground background.
Did early ones have limits?
Yes, they could tumble, become unusable in extreme attitudes, often had a caging knob to reset them. Modern ones are generally non-tumbling, good through 360 degrees.
What about the directional gyro, the heading indicator?
The DG, or HI, provides a stable heading reference. Driven by vacuum or electricity, its gyro rigidity keeps it pointing in one direction in space.
Better than a magnetic compass in some ways.
Yes, not subject to those dip errors, but it suffers from precession slow drifting over time due to friction.
So it needs resetting.
Correct. Needs to be periodically realigned with the magnetic compass during straight, level, unaccelerated flight using the adjustment knob.
And the turn coordinator, combining turn and bank info.
Right. Shows rate of turn, yaw, and rate of roll. Its gyro is mounted tilted upwards, maybe 20-35 degrees.
Why tilted?
Makes it sensitive to both rolling into a turn and the steady rate of turn once established. Display usually shows a mini airplane that banks with the roll. Rate of turn shown by wing alignment with index marks.
How?
Usually electric, sometimes vacuum. Important to distinguish it from the older turn and slip indicator.
How's that different?
Turn and slip has a vertical gyro, shows only rate of turn, has a separate ball inclinometer for slip skid. The turn coordinator gives a more combined sense of the turn coordination.
Okay, let's move to autopilot systems. Taking over the flying. Primary function.
Basically, to automatically control the flight path without constant pilot input. Maintain selected attitude, heading, or course.
Same purpose.
Reduce workload and fatigue, especially on long flights or in IMC instrument conditions. Offers manual modes where pilot commands changes via the autopilot, and automatic modes where it maintains a selected parameter like altitude or track.
And they vary in complexity. Different axes.
Oh yes, simple single-axis ones, wing levelers, just control ailerons for roll. Two-axis control ailerons, roll, and elevators, pitch, for heading and altitude. Three-axis adds rudder for coordinated turns and yaw stability,
And more advanced systems.
called Automatic Flight Control Systems, AFCS, on bigger planes. Control all three axes, plus maybe auto trim, flight director integration, auto throttle for speed, complex profiles like climbs, descents, approaches, even auto land.
And flight management systems, FMS.
Even higher level, lets pilots pre-program entire flight plans that the autopilot and related systems execute.
What's the basic principle they operate on? How do they stay on track?
Error correction. When the plane deviates from the selected state, heading, altitude, attitude, the autopilot senses the error using gyros, accelerometers, pressure sensors.
And corrects it.
Right. Generates commands to the control surface servos, ailerons, elevator, rudder, maybe throttle, to move them and eliminate the error, returning to the desired state. Can be position-based, minimize deviation, or rate-based, react to rate of deviation. Rate-based, often smoother.
What are the typical components of an autopilot?
An analog system usually has sensing elements, gyros, accelerometers, pressure sensors, an autopilot computer amplifier, processes inputs, generates commands, output elements, servos moving the controls, and command elements, cockpit controls for pilot input.
Modern digital ones.
Often use MEMS gyros, solid-state accelerometer, digital processing. Servos can be electric motors with gear clutches or electro-pneumatic hydraulic on larger aircraft.
Safety features.
Crucially, an autopilot disconnect switch, usually right on the control wheel for immediate manual takeover. Also feedback elements telling the computer the control surface position, preventing overcorrection.
Can you give a basic overview of how it controls each axis? Roll, pitch, yaw.
Okay, for yaw heading, rudder. A yaw gyro detects deviation from heading. Signal commands rudder servo. Rudder moves. Feedback signal tells servo when to stop as error reduces.
Ailerons for rollback.
Similar. Roll sensor, often in the AI, detects deviation from desired bank. Signal commands aileron servos. Feedback helps stabilize.
And elevator for pitch altitude.
Manages pitch attitude. Can be linked to an altitude sensor for altitude hold select. Deviation from target pitch altitude signals elevator servo to correct.
Modern AFCS sound incredibly integrated.
They are. General aviation AFCS often fully integrated with digital AHRS, nav receivers, often a distributed architecture intelligent servos at each control surface, doing some processing, communicating digitally, maybe no single central computer, enhances reliability, reduces wiring.
Let's turn to electronic instruments now. They've really changed the cockpit look.
Absolutely. Big advances in how info is presented, more flexible, integrated, better situational awareness. The Electronic Attitude Director Indicator, EADI, is a good example.
Advanced AI.
Yeah, shows pitch roll, but overlays other info guidance cues for approaches, flight director commands, can show enunciations for autopilot modes, nav sources, consolidates a lot of data.
And the Electronic Flight Instrument System, EFIS, takes that integration further.
Definitely. EFIS uses dedicated signal generators driving both the EADI and the Electronic Horizontal Situation Indicator, EHSI. Displays were CRTs initially, now almost always LCDs.
Replacing traditional gauges.
Effectively replaces the traditional AI, DG, sometimes airspeed and altitude too, puts it all in a versatile electronic format.
I've also heard of ECAM and ICUS. What do they do?
ECAM, Electronic Centralized Aircraft Monitor, and ACAS, Engine Indicating and Crew Alerting System, are sophisticated systems displaying aircraft system info, warnings, cautions. ECAM might also show electronic checklists.
Focus areas.
ECAS primarily focuses on engine data, RPM, temp, pressure, and other key airframe systems, fuel, electrics, hydraulics. ECAM is similar, often with more system diagrams and procedural guidance. Even with these, you usually still have some traditional backup gauges.
And the Flight Management System, FMS, kind of pulls it all together.
Very much so. It's the brain, integrating data from sensors, nav systems, databases, manages the flight plan, interacts with autopilot, flight director, auto throttle, allows programming complex routes, optimizing performance. Big jets usually have dual FMCs and CDUs for redundancy.
Now, safety warnings. What kinds of oral warnings alert pilots?
Various audible alerts for critical situations. Examples: wrong takeoff configuration flaps, overspeed make warnings, cabin pressure loss, landing gear not down, fire warnings, collision avoidance alerts from TCA. Distinct sounds to grab attention immediately.
Timekeeping is also important. Requirements.
For IFR flight, you typically need an FAA-approved time indicator clock or chronometer. Pilots use it for timing approaches, fuel calcs, navigation backup.
What about traditional clocks?
The mechanical 8-day clock was standard for years. Good, because it didn't need electrical power, often had an elapsed time function for timing segments.
Finally, let's briefly touch on instrument mounting and markings.
Okay. Instruments are usually mounted using flange or flangeless methods, securely held. The markings, colored arcs, lines on dials, airspeed, temp, pressure, attached, give instant visual cues.
What do the colors mean?
Typically, green arc is normal operating range. Yellow arc is precautionary range, use with caution. Red line is a limit never to be exceeded, standardized visual language.
And of course, all these instruments need regular maintenance and testing.
Absolutely essential for accuracy and reliability. For IFR, the altimeter and pitot-static system need testing and inspection every 24 months by certified shops. Checks accuracy, leaks, altitude reporting.
Other checks.
Electrical tacks checked for sync, especially at idle. Magnetic compass needs regular inspection, accuracy, free movement, fluid level condition, lighting. And it needs periodic swinging to check and correct deviation, especially after maintenance. Results go on the correction card.
What about vacuum systems?
Monitor the suction gauge. Check for leaks or pump issues if an instrument acts up.
Autopilot.
Need thorough operational checks after install or maintenance. Smooth control movement, alignment, cable tension. Check pitch trim, manual override. Always follow manufacturer procedures.
And those new LCD screens.
Need special care. Harsh cleaners can damage the anti-reflective coatings. Use approved methods.
Well, we have certainly covered a huge amount of ground on aircraft instruments, from those very early mechanical gauges to the incredibly complex electronic systems today. It's so clear how vital they are for safe and efficient flight.
Indeed. And, considering the way automation is increasing, it really makes you wonder, how will the role and design of flight deck instruments keep evolving?
That's a good question.
As systems handle more tasks automatically, what does that mean for pilot skills, for situational awareness? What's the future balance?
A really fascinating thought to ponder. If this deep dive has sparked your interest in any particular area we discussed, definitely dig deeper into those sources you sent. And as always, if any follow-up questions come up, just let us know.
Absolutely.
Until our next deep dive, fly safe.